Hey, welcome to Networks Part 4. This is coming to the end of Networks, and what have I got here for you? Shortest or longest path? Why would you want the longest path? Uh-oh. Is it happening to you? Are you putting on a little bit of weight like I am? Maybe you've got to go further. Maybe that's a reason for choosing the longest path. I don't know. We might look at some more practical solutions or reasons for that in a minute. But I'll look around the diagram. So you've got an old one that we've seen before, some towns here, and you might need to go through every one to sell something, and you want the longest path, but not to backtrack. Okay, and over here we might want the shortest set of edges, if you like, or spanning tree that can connect all these. What's the best way of connecting all these computers maybe, or drinking fountains to a water supply, something like that. So all sorts of interesting problems. Usually, I suppose it's the shortest path to get from the start to the finish of something. But there are other practical situations. So let's have a look now at all of these. So let's have a look at longest path problems here. Sometimes we need the longest path through a network. This may be to maximise profits or points collected on the way. In other words, we really, if we go to all the towns and try to sell some stuff, then we're going to make more money. But we don't want to go backtracking, because if you kept going backwards and forwards, the longest path would be infinite. We could go backwards and forwards continually between nodes, and that would increase the length forever. We don't want that. We can therefore only find longest paths if the network is directed, or if we're not allowed to return to a node previously visited. So it's finite. Otherwise, you could just go round the circuit. Okay, so what I want you to do in this next one is to actually do it by trial and error. So come down, let's have a look at the problem. A hardware salesman needs to travel from Adelaide to Mount Gambier. Here it is for a meeting. And based on previous sales, he estimates the amount of money he can earn along each section of the route. Which way should the salesman go to maximise his earnings? So you don't want to go backtracking. You want the longest path through the most towns, but not going over the same points. Okay, so leave that with you to see what you come up with. Just trial and error. Try and work it out for yourself. Right, pause the presentation and have a go. Now I'm going to take you down to the answers. I know, here's another question for you. The network shows time minutes to drive between intersections of the street. Okay, give the shortest and the longest times here. Okay. Don't know why you'd want the longest time, but we're going to do that as an exercise. So try that also, just by trial and error. Right, let's have a look at the answers then. Here they are. And check them off and see if you agree. Go back and check your work again. Right, let's go on to what is probably more practical, and that's shortest connection problems. So we're seeking the most efficient way of joining vertices so that paths exist from any vertex to any other vertex. Vertices do not need to be directly linked. They must all be somehow linked. We don't need to have it as a circuit. You don't have to be able to go around and back to the same point as such. It's a little bit different, this one. So where you're linking computers and printers in a network, or connecting a set of pop-up sprinklers to a tap, or a group of towns with telephone, water or power lines. Okay, now what we're going to do there is called a spanning tree. It's not a circuit. It's a simple graph with no circuits, but connections exist between all vertices, not necessarily next to each other, but maybe connected like this, and down here, and maybe there. We wouldn't need perhaps this one, would we? We don't have to have a circuit. And then if that's the water supply, or maybe this is the water supply, we'd tend to lead it there and then come out. The question is, what is the best way of spanning all of those nodes, all of those connecting points? So we're looking for the minimum length spanning tree to keep the pipe work down or the power line lengths down. Okay, so that's the idea. Let's have a look at what we might do with that. Here's one here as a little investigation for you. School has added 4 new drinking fountains for its students. Okay, the waters come from an existing purification system at A, so here it is. The points B, C, D and E mark the location of new fountains. All fountains must be connected to the purification system, though not necessarily directly. Okay, so in other words, you don't have to do this. You want the shortest distance spanning tree. Okay, to get all of them connected with the minimum length of pipe. So using the scale on the diagram, so you can measure off the screen here, just because all you're interested in is which length is bigger than the other. Trial and error, find the minimum length spanning tree for the network which gives the shortest length of pipe. So it won't be joining them all, like I said before, directly to A. You should be able to shorten it there. Okay. All right, have a go, and you might talk to classmates and teacher about what is the minimum length. Now, by this time, you must be saying, I would guess, hey, Huddy, this is maths. All this trial and error, that's a bit silly. How would you do it mathematically? So that's what we're going to do in this presentation. Have a go at some mathematical ways. Just for the moment, though, in this next exercise from Hayes and Harris Publications, there's a little bit of practice with trial and error to see if you can do it and think about how to keep the lengths down. And that's going to lead us into an algorithm, a mathematical process, if you like, or method for finding the shortest path. Okay, so have a go at these two and pause presentation, and I'll bring up the answers in a minute. Okay. 7C5 now. Oh, I haven't got the answers there for that one. Oh, that's not good. Okay, let's slip on in to the algorithm part of this. And this is Prim's algorithm, after the person who actually developed this method. So what we're going to do is start with any vertex and we add vertices one at a time. Notice there is no circuit or network diagram at all at the moment. So it's quite good if you've got a scale diagram where edges are not already drawn in, just the towns or the points of the fountain. And we add a new vertex with each step. And so you won't form a circuit. There's no reason to come back to the beginning. This is called a spanning tree now. You need connections between all the points, but you don't have to travel around and form a circuit. You don't want a circuit. So what's the steps? Start with a vertex, join this vertex to the next nearest, join on the vertex which is nearest to either of those already connected. So each stage you look for the shortest distance. Repeat until all vertices are connected, and then you add up the lengths. So it's a fairly simple idea. Don't move before you actually make sure that you're moving the shortest way, the shortest distance. Let's have a look and see about an example. I'll go through this one with you. This is school fountain one, back on the first screen. So what are we going to do? Choose to start at E. Okay, come down here with the drawing from the book here. So we choose to start at E. You can choose anywhere. We've chosen E. So what's the closest point? Well, just by looking at this scale drawing, you can see D is closest. So we'll go there. So DE is our first part of the solution. Then from D, B, you could measure that, is closer than A or C. So we're going to go to B. And then we could go to A or C. So A, though, is clearly closest. So we'll go there. And then, of course, we've got to add them all up. So we'll go to BC. Okay, so we include BC by default. You've got to include the last one. But all along the way, we've kept all this to a minimum, and then we've just got this one here. And that's just a process, okay? You might try it a different way and just check, would it have been better to start at B? Would it have made a difference? Okay, we've got a minimum length of 400 here. So you could try this. So it's a little algorithm, a little method, if you like, of finding the shortest connecting tree or spanning tree. Okay, so let's have a look at another person's algorithm, nearest neighbour algorithm. That's another way of finding the shortest spanning tree, if you like. But this time, you might have a network already in place. And then you're going to remove the longest edges one by one without disconnecting the graph until you get the minimum length spanning tree. So you go back, it's a backwards one, isn't it, really? One is creating the edges and creating the tree. The other one has got a lot of connections and you're removing the longest ones without isolating a node. Okay, so here are the steps. Locate the longest edge which can be removed without disconnecting the graph. That is, all the nodes have to be connected. It's got to be a spanning tree, got to span it. Okay, remove that edge. And you keep going until the removal of any more edges will disconnect the graph. And then you add up all the lengths of what's left. So one's forwards and one's backwards. One starting with just the nodes, the towns or whatever, the fountains, and putting lines in and building it up according to the shortest method. And then the other one, nearest neighbour algorithm, takes an existing diagram apart by removing the long ones. Okay, let's come down and have a look at an example of that one. Nearest neighbour algorithm to find the minimum length spanning tree for this one. So let's have a look and let's follow the solution here. We look around and the longest edge is DG. Okay, now where is DG? Well, that says here. So they've just removed that. Okay, sorry, I should have started up here. So that's the longest one by the 15. So we get rid of it. Okay, we get rid of that. Now, are they still all connected? Yep, so that's okay. Next longest edge, let's have a look. We're looking for the biggest number. Well, here it is here. And can you, FG. FG is that one. So they've removed it. Is everything still connected? Yep. The next one is the 13 here. But we can't do that. Okay, we can't remove that one because it would leave F disconnected from the others. There's another one over here though. And can we remove that? Yes, we can, because it will still leave A and H here connected. So we've got rid of that. Okay, what's the next one? Let's have a look. 13 over there, we've discussed that. Now, what about the 12s? There's some 12s. This one and this one. We can't remove this because it would leave these points disconnected from the spanning tree. We can remove that one. So come down and have a look. That one's removed now in here. All right, we're getting there. We won't be able to remove too many more, I don't think, because it'll leave points disconnected. Okay, so this is it. So we could add them all up. Here it is, 10, 8, 7, 10, 13, 12, 11. It's 71 metres of pipe work or whatever to make sure all these are connected. Or whatever the things are that the nodes are representing, whether they be towns and this is distances or whatever. Okay, so we don't want to make more roads than what we have to or lay more pipes than what we have to. So this is called a spanning tree now. All right, let's have a look at some problems and see what you think. Okay, so here use prims and then the nearest neighbour one to get the minimum length spanning tree. So this time, remember, we're not working with circuits. We must have connections between all the nodes and we want them to be the shortest. Okay, 1 and 2 and the computer network problem, you can go back and look at the earlier presentations or in your textbook for that one. Okay, and here's some more. Broadband cabling, this is pretty topical. That's important. And then an alpine area here, little problem. Find the roads to get the minimum total length to get to all the towns. Okay, it's hard to clear the roads if it's trying to get into a spot and it's isolated with snowfalls. Okay, have a go. Come down now. Number 6. Okay, flight distances. Okay, weather might affect this, however, so we won't be able to take account of that. Number 7. Interesting problems, aren't they? And then number 8. All right, communication networks. You don't join everything to everybody. You can use the lines that make a minimum length of cable to connect these spots here. All right, let's have a look at the answers. Question 1. Did you get those numbers? Question 2. Question 3 and 4. I'll just bring up question 5 in a minute. Question 5. And then question 6. Got 7 on there as well. And question 8. Okay, so it's an interesting application, isn't it? Networks, there are many interesting applications of them. Just remember the difference between circuits and paths and the idea of a spanning tree, but you don't have to do a whole circuit for that. All right, now there is one more final presentation in the networks idea where we're going to look at another representation leading into matrices. So we're going to represent a network in yet another format and see what you think. It's all good problem solving. So I hope to catch you then. At the moment, cheers for now.